All right, let's get going. We've made it to another Monday. Amazing. Actually, I have a Monday here. So here's what we're going to do today. So Wednesday is our mid-year exam, right? So we're just going to do a little review, kind of step back a sec, look at what we've learned, go over some concepts that I think you should concentrate on for the mid-year exam. And we'll go over, we'll look at some questions from last year's mid-year exam. Okay, I'm kind of like 95% done with this exam, and the format is very similar. Some of the questions are obviously different, but the format and kind of the big structure is very much the same. Okay, let's see. Homework 4 is due Friday. I was thinking about it the other day, so I'm actually going to be out of town until Sunday. We are not going to start grading them until at least, say, Monday. I see some smiles. Do you guys, if I gave you an extension until Sunday, would that help things a little bit? Okay. I will formalize that on Piazza. But that's a couple extra days. I know this is a busy week for everybody. I kind of realized that from the 5 or 10 emails I've gotten saying, my week is so crazy, which I get. Trust me, I understand that. And we've got our mid-year in here, so we'll try to we'll do that. All right, questions before we get going? Okay, so for the review, first of all, we'll do a little quick tip of the day. You guys know about zip files, right? You can zip files up and send them to yourself. So let's say that you did Comp 11 and you say, you know what, I don't need to take up all that space on the homework server for Comp 11. What if I wanted to zip up my Comp 11 folder and then send it to myself? So A, I have a backup of it forever, and B, so it doesn't take, I can delete it from the homework server if I want, etc. You can do that. We'll look at that, and then we'll do more review. Okay, let's look at the, actually, I don't know that I have any, yeah, here we go. I do have a little thing on this. So you can actually use the zip command to actually create a compressed zip file of your folders. Let's say that you didn't run the little clean command. You had core files in there. You could actually run this command, say zip-r, comp11.zip is the name of the file you're putting stuff into. And then the comp11 directory, let's say you're in the desktop or one directory up from the comp11 directory, do comp11.zip and then comp11/star. That says everything in comp11, and then do it recursively. If you have other folders in your comp11 folder, it will do that. -x star core star says anything that has the word core in it, don't put it in this zip folder, right? And then that would do it. And then now you're going to have a big file called comp11.zip, and you can remove it. But before you remove it, you might, then you can remove the actual comp11 folder structure if you want as well. You could leave the zip file on there on your computer, or you could transfer it to your own computer, etc. Yeah, Zoe. This is the name of the file now that's the big zip file. Right? I'll show it to you. Yeah, I'll show you an example. So let's go on to the homework server, and let's say that, let's see, do I have a comp? I might actually have a comp 11. Oops, comp 11. I do. OK, it's got a bunch of stuff in comp 11. So if I wanted to do this, I would type zip-r, and the internet doesn't seem to be working very well right now. There we go. Zip-r, and then the name of the file, comp11.zip, which I'm going to create, right? And then comp11/star, and that says take everything in the comp11 folder and put in the zip file. -x, if I happen to have any core files, that will not put core in there, and it will tell you what it's doing. And it says, OK, look, I added all this stuff. And now, if you look at your folder, now there's a, whoops, can't see it. Here, I'll just bump it up. There is a comp11.zip file in my folder now that I could now transfer to myself. Okay, and it's a good way to keep a backup. It's a good way to compress everything to one location, etc. I did have a student a couple years ago, or a couple semesters ago, who tried this for some reason, and then for whatever reason she typed the command wrong. This ended up as a 0-length file. Then she sent it to herself and then deleted all of it, and then didn't realize this for many months, and the backups were already gone. So be careful that your file actually has stuff in it. Right? You also might want to, when you get it to your computer, unzip it and then see if it's still there, and then keep the file still. Question? Which file was deflated 2%? I don't know. Let's see. Probably one of the binaries or something that's hard to do. There we go. No, a PNG file. Yeah, so there's a file called asteroids.png. I don't know what that is. Asteroids.png, and it was only deflated 2%. You know why? Yeah. Yeah, they're already compressed just about as much as you can get, right? Same with JPEGs, almost completely compressed already, so you can't compress them again. It would be kind of cool. I used to think that, like back when I first looked into these things, way back when I was like in high school, I was like, whoa, if you keep, like, what if you compress a compressed file? Does it get more compressed? Well, it might by 2% maybe, but then eventually it's going to stop compressing anymore because you've taken all the extra information out of it. That's the whole point of compression, right? When you get to Comp 40, you will do a whole project on compression, and it's kind of fun, actually. Yep. Anybody else? OK. So that's the zip function you can, or zip command. You can use that to zip up your stuff. OK. All right. OK, so the midterm. So here's some general study tips. Obviously, you can study however you normally do. You do get a one-page back and front handwritten set of notes. I mentioned this the other day. You can't use your you can't use some sort of like super magnification printing technology that shrinks it down and whatever. You got to actually make it handwritten. Blah blah blah. Studies say that it helps you study anyway, et cetera, et cetera. So you can use that. OK, review all the slides, notes, codes, samples that it provided, videos if you want. Obviously, you probably don't have like 20 hours to go review all the videos, but you certainly could with the ones that you didn't understand. Go over your homework assignments. At least kind of figure out what we asked you to do, because I could ask you things specifically about your homework assignments, and I could say, you know, how would you implement this, or how would you have re-implemented this, et cetera. And review all the labs. Just go read the code that you provided. You don't have to know all the stuff in the maze CPP file that we gave you. You don't have to know that. Just know the functions that you created. Right? In the maze one, we did what? We did a breadth or a depth first search. So go review how that works. It's a recursive search. You used a stack, et cetera. Right? OK. So do that. Those are kind of the big tips on how to study. I should have put this before the slide. OK, remember the other day I mentioned this in one of the hardest parts about the homework assignment is removing this double child node. Step back a second. This is kind of review as well for the mid-year, because you do need to know these things. But let's talk about how we're going to actually do this. And I want to just go into a little bit more detail than we did when we said, oh, recursively remove the child, et cetera, et cetera. OK? So let's do it. We'll do an example. And you have to consider a couple things. First of all, when do you actually move the data when you're doing a double child remove? Remember, for a double child remove, 5, 3, 7, right? If you're removing the 5, right, and it's got 2 children, we had an algorithm to do that, but it ends up being that the 7 replaces the 5 here like this, right? The 7 replaces the 5. But you have to do that in a particular order, or else your recursive remove function for this one might fail. OK, if you haven't thought that through yet, think it through with me now and then implement it later. OK? And then you also have to think about, especially in our case, what if the 7 had multiple copies of itself? Like there were like 4 copies of 7, right? What needs to happen is the whole node needs to move up here, right? And then you remove this. What would happen in the generic remove function if you removed the 7 right now? Let's say it had a count of 3. What would happen if you were to remove 7? Count would be 2, right? Then count would go down to 2, and that would be removed. But not in the case where you're removing this one. If you're recursively removing this one, the whole node and all of its duplicates have to get moved. OK, so that's something you have to consider. OK, let's do an example of both of these. All right. OK, remove 17. OK, remove 17. Here's what I'll do. I will write down just the part that makes a difference here. Actually, I don't even think anything. The 14 doesn't really, well, means a little bit. 16 and 53. OK. All right. let's go much more in detail than what we did in class. Like before we said what? What's the algorithm for removing the 17 if it has 2 children? I mean, first you have to check if it has no children, then you have to check if it has 1 child, and those are separate remove cases. But let's say you all of a sudden get to a case where 17 has 2 children. What's the general algorithm? Somebody remind me. Yeah. Yeah. Okay, so you find the minimum of the right subtree, which in this case happens to be this one right here. Okay, so this is the minimum of the right subtree. Then what's the next step? Do you know it? Replace 17 with the minimum of the right subtree. So this becomes 53. And then what? Recursively delete this one, which means we're going to get rid of this one. Now, the devil's in the details, as they say on this. Because this happened to be the child that we're now replacing it with, when you go to recursively delete 53, this is where I'm saying we got to get a little more in detail. If you go to recursively delete 53, how do you know whether 53 right now is to the right of its parent or the left of its parent? Let me change this back for 1 second. How do you know if 53 is to the left of its parent or to the right of its parent? Yeah. OK, that's one way to think about it. It was the minimum of the right subtree. OK, so that's a good point. Let's say you didn't know that it was the minimum. Let's say this is we're just removing 53. How do you know that it's a right child? Yeah. OK, because 53 is greater than 17, right? So if you were going to, this is now down at the level of actually having to code this. We have to, if we're removing 53, what node becomes null? What pointer becomes null? 17's right becomes null. And the only reason, well, really the reason that you knew that 17's right became null and not 17's left is because A, 17's right pointed to 53. That's one way to figure it out. Or 17 is less than 53, so 53 must have been a right. OK, bear with me on this. Yeah, question?
But do you make the null after you remove the function or before that?
Well, this is where you have to figure out. You have to figure out what to do. You have to figure out the details of that. And this is going to be specific for your code. But let me show you that one thing that people generally forget to do. If they're removing 17, and they say 53 now replaces 17, if you're trying to figure out if 53 is to the right or the left of 53, it's impossible to do because they're the same value, right? Or sometimes it might go to the left depending on how you code it. Sometimes it might go to the right. So you've got a problem there. So what's the solution to this? We just need to modify our algorithm just a little bit in this case. What do you guys think? Anybody have any idea what the solution to this is? Maybe I'm not being specific enough about what the problem is. But you will figure this problem out soon enough. So I'll explain it to you, and then you'll go back. And when you're doing it, you'll go, oh, I get it. Now I know what's going on. If I recursively remove 53 after I've changed this value to 53, we've got a problem. Because you can't decide. It's harder to decide whether 53 is a right child or a left child of this node. So why don't you remove this one before changing the value? OK? In other words, keep some temporary data around. This data is 53. The count is 1. Then recursively delete this while 17 is still 17. Then replace 17 with 53 and a count of 1. OK? Does that make a little more sense? Or at least, do you understand that part of it? You may not get why quite yet. But if you will when you end up coding this. You'll go, oh, that's what Recursion's talking about. OK? First things first, remove this one. And you can do that recursively if this one's still 17. You don't have to change anything. OK? Yeah, question?
Can we do a way to store 17 somewhere else and then compare the two?
Yeah, you could do that too. But the only problem with that is then you're going to have to update the remove function to know that you've kept 17 stored somewhere. It's just easier after you do the remove to say this one's value gets 53. You can figure it out that way, that's fine, but it's going to be a little, I think it's going to be a little trickier. OK? All right. The next one is a little bit trickier as well. what if we had this case where, and this is what I mentioned a little bit earlier, 1753, where it's got a count, let's say the count equals 3. If we're removing 17, what's the issue now? We already kind of mentioned it, right? I guess that's rhetorical because we already mentioned it. The issue is if you try to delete or remove 53 recursively, you end up with 53 here with a count of 2, and you end up with 53 here with a count of 1, or with a count of 3, or however you copied that one up there. That's the problem. So then you need to figure out, OK, at what point do I need to actually remove 53? You may have to write another little part of your function that says, OK, I'm dealing with a special case here of removing recursively, like remove all recursively or something like that. You might have to rewrite that function completely. OK, but the point is, if we're doing it this way, if we're moving 17 and that has a count of there, remove 53, the whole thing, including all the count, keep track of the count being 3, put it here, and the count is now 3. OK, and this one's going to be gone. You see the problems with that? I've seen a lot of people who end up with that concern when they end up trying to do this. OK, questions on that? No? OK, all right. If you do have questions, put them on Piazza or email me. Okay. All right, back to the review. So mid-year. So here's the kind of problems we'll have. By the way, I'll go over it in a few minutes, but I did put last year's midterm on the web so you can see it and look at it and kind of get a feel for what the test is going to look like. There's going to be some short answer questions like explain a case where a linked list is better than a dynamic array, et cetera. You're definitely going to have to find some bugs. Bugs are tricky to find when you're staring at code, right? There's definitely harder bugs than others. The hardest bugs to find are the ones where we forgot to put something in. Like we forgot some code, and you go, oh, if I'm doing this function, I'd better remember to do x, but we forgot x in R, or we didn't put x. So that's one of the trickier ones. OK, but bug finding, you got to do that. We will have some short code writing. There will probably be a little bit more code writing than on previous exams. Some of the feedback I got was, oh, we didn't do enough code writing on exam. Well, it wasn't really feedback from the students. Nobody really complained about that. But I think in the end, it probably makes a better test if you do a little bit more code writing on an exam. OK. Explain what code does. Like you might have to say, hey, this code does this, this, and this. What does this print out? What does this, what are we trying to accomplish here? You definitely have to determine big O bounds. Now, somebody asked a Piazza post about this. I didn't see if it got answered yet. I was holding off to see if anybody else wanted to answer it. Somebody asked a good question about how do I determine what big O is if you've got a particular piece of code you're trying to look through. And it's a little even more tricky when you have recursive code that you're looking through. OK, so we'll go over that example on last year's mid-year. OK, all right. And then you have to explain some C++ stuff, like why do we need a destructor, or some of the stuff for the operator assignment overload or copy constructor. By the way, you'll be practicing that in lab tonight. Pre-lab is up, by the way, so hopefully you'll be able to get a chance to do that before lab today or tomorrow. Everybody's going to lab now, right? Actually. Well, I could come up with, I could describe a data structure for you, and you would have to explain it to me. That would be hard, but it's not going to be something you aren't prepared for. I'm not going to say, hey, tell me what a hash table is, and we haven't even talked at all about that idea, right? I mean, I could set something up and say, it wouldn't be a hash table, but I could set something up. I could say a 2-3 tree has the following invariants, right? That's a new kind of tree, and you could do that, right? Actually, they gave that one on a mid-year a few years ago, and the students hated it. But I won't do that. I won't be that mean, I hope. All right. Anything else? Yeah? AVL trees are on the exam. We did a lecture and a quarter on them. I think we'll do another practice today. It's not going to be, you certainly won't have to code anything with AVL. You'll have to basically insert into an AVL tree. I want you to know how to do that rotation business. OK. Anybody else? OK. All right. Let's go over some specifics. So here's all the topics we've covered so far. C++, we've done some memory management stuff. That's kind of the only new real C++ stuff. References, I suppose, we put in there. Let's see, what else? What other memory management stuff did we have? C++. I'm not going to ask you about const or anything like that. Don't worry about that. We talked obviously about dynamic arrays. We did a whole project on that. Doubly and singly linked lists. Remember, I'm not a big fan of linked lists, so I'm probably not going to test you too hard on those. Although last year I did have a mid-year question about that. And then recursion. You really should know how to write recursive functions. Okay? There's going to be at least one on there where you have to write that, and you might have to understand some recursive functions as well. Stacks and queues. We had a whole project on queues. Stacks are fairly simple, but you should understand both. You should understand those. We'll go over that. Trees. So general trees are like non-binary trees, right? Then binary trees and binary search trees, important. And then, of course, AVL trees, which are just a special case of binary search trees. And then asymptotic notation, okay, which kind of permeates the whole class. All right, those are the big topics. Let's look at some of them in detail. C++, yes, you do have to know what destructors do and why we use destructors, right? Dynamic versus automatic memory. We never really used these terms in class, so I'm not going to use those terms on a test. But basically, the idea is when you use the new keyword, you're dynamically allocating memory, getting it from the system. And when you don't use new, when you just say q, for that example, stack s or something, right? Then you're using what's called automatic memory, where the compiler handles most of the stuff for you. Okay, and then you also need to know kind of the difference between abstract data types and data structures. Okay, kind of the big picture on those things as well. All right. Sample question for you. Why don't you do this right now? Write somewhere, or explain it to your neighbor if you want. Why is a destructor necessary? When is a destructor necessary? And when is it OK to use a default destructor? Go ahead, take 2 or 3 minutes and explain that to your neighbor. OK, who thinks they have a good one-liner answer on when you have to use a destructor? Go ahead.
When you create a dynamic memory, you have to write a destructor to delete it and free up, and we haven't done that.
That's a pretty good answer. I would accept that answer. But it's a little more specific than that. The answer was, for those who didn't hear, when you request memory using the new keyword, you have to, at the end of your program, clean up after that data. And so you have to use delete on it in that point. Now, sometimes you may not have to do that. Let's say you were in a function, and for some reason you said new data and then delete at the end of that function. As long as there's no excess data left over when your program's ending, then you don't need then you can use the default destructor. Okay, so that's a good answer. The answer is basically, if you've used the new keyword, be really careful. Right? If you use the new keyword, at some point or another, you will need to delete that. And if it happens to be when your program is ending, that's what the destructor is all about. Okay, question?
So if you have using C++ kind of generic classes, so if you have a kind of a queue of pointers, how would you, is this a built-in deconstructor that cleans up after themselves?
Yeah, you have to come up with the logic to do it. So if you have a queue of pointers or something like that, right? We didn't actually talk about it, but let's say you made a queue and it had pointers in it. And here's your queue, and this one points here, and this one points here, and this one points here, and this one points here. Okay, at the end of in your destructor, you need to walk through your queue. If these were all using new, like this is a node or some object that you use new to create, then you need to walk through your array in your queue and delete each one, right? That's what you have to do. So yeah, you have to do that. And then depending on whether or not this is a dynamic array itself, you might also have to delete the dynamic array too. Okay, you kind of have to do both things. All right, yeah, good question. Okay, yeah.
Just curious, are there any times when you have to not have a default destructor, but not using the new keyword?
Are there any times where you use, well, if you use a thing called malloc, which is another, it's kind of like new, you may have to do that, but otherwise not really, no. In our class, we're not going to use malloc. When you get to comp 40, you will. There's no such thing as a destructor in C, so you have to manage that a little bit, you have to manage it a little bit differently. But yeah, normally no. If you don't use the new keyword, you're probably not going to use a destructor. Need a destructor. Okay. Anything else on that? Yes?
So the default destruct is only used if you've already deleted all of the memory that you called with new.
Right. If you've already now, keep in mind, why do we care about new? Right? Like, why do we even use new? Because our class might have its own data structure, like an array. And so we need to use new to create that. And the only time that's going to get deleted is when their class is about to be destroyed at the end of your program. So that's when you would need it. We also might use new in, remember, the expand function uses new. And it's the same idea, but basically it's saying, here's an array that's going to last longer than the end of this function. That's when you do it. So to go back to your question, as long as you've cleaned up and you know everything that you use new on is gone, you don't need a destructor to do any more cleanup. Most of the time you do, though. Okay. Anybody else? Okay. All right. So that's the destructor. Okay, let's go over the static and dynamic arrays. Just a little quick review here. You should know the difference between static and dynamic. If you say my array 10, right? If you say int my array 10, right, that would create a static array of 10 integers for you. And you would not need to use to delete on that. In fact, you couldn't, right? The compiler handles all that for you. Problem is, when you say this, it's only good for the length of your function, not outside your function. Okay? And dynamic is obviously when you use new. Arrays, the nice thing about arrays is that we can index into them using in constant time. If you say my array 4, you get that. It only takes one step to do that. You don't have to walk through the array. You might be in the process of walking through the array, but that's a different story, right? If you're searching through an unordered array, yes, you need to walk through each one, but each lookup is only one time step, if you will. Okay? Why are arrays good? Anybody want to answer that? Why do we like arrays? Maybe we don't. Yeah?
Good for inserting in the back, good for having a time where you can tell you how many you want to add, and you may want to add more later.
Yeah, or it's funny, arrays aren't necessarily good if you want to add more later, because you do have to copy and expand them. But yeah, I will agree that they're basically fast, right? I mean, that's kind of the idea, is that they're fast and they're in one location, like they're concurrent in memory, or contiguous rather in memory. Yeah.
You can access the data non-linearly as well.
Yes, that's a very good point. You can access the data non-linearly. In other words, if I have my array and it's got 1, 2, 3, 4 in it, I can look at 4, or I can look at 3, or I can look at 1, or whatever you want. Unlike in a linked list, where you have to start at the beginning and walk through the whole thing. Yeah, absolutely. Random access is very important it's called random access, which is very important for arrays. Okay. Downsides to using arrays? I like what you were saying about inserting before. Yeah.
Fixed size.
Fixed size, yeah. You do have to expand them if you want to use an array. Many other languages do that for you behind the scenes, right? If you're working in Python or if you're working in Java with an array list, right? That'll happen behind the scenes. It's still happening. You still have an array back there that somebody's written a program to expand it, just like we did. But it's definitely, it's easier if you don't have to do that for yourself, right? But yeah, absolutely, it's fixed size. Okay, what were you were saying about inserting at the back is good. What's not so great? Yeah, inserting at the front of an array, you have to move everything that way, which is what behavior asymptotically? N behavior, right? Linear behavior. You have to move everybody over. And you have to do it right, too. You can't be like, think you're being clever and just move this one into here, and this one into here, and this one into here, because you'll overwrite them all, right? You have to move this one here, then this one here, then this one here, and you have to go backwards. It's kind of a pain. OK. We talked lots about expanding dynamic arrays, and then we just talked a little bit about the asymptotic behavior. OK. Here's a type of question. Write an insert function for a dynamic array. An insert, let's say, at the beginning, right? So you would have to write the little loop to do that. What's the first thing we always check in an insert for a dynamic array? If we need to expand, yes. OK, you're going to do that. And then that gets handled in a separate function. And then you need to do this business where you're going to move, like go backwards to the array and move this one here, and this one here, and this one here, and this one here, and this one here. OK? Yeah?
So this kind of problem would be write the expand function inside.
No, I would probably say you are allowed to use the expand function separately. Like just say expand, and it will expand. OK? Yeah. Good question. Anybody else? I think we've covered a lot on dynamic arrays. And by the way, this kind of goes back to, why do we teach this class in C++? If we taught this class in another language like Python, you would never get to these details. Some of you guys are saying, I don't care about those details, right? But we kind of want you to understand the underlying data structure. Because if you're taking a Java class, for instance, and you say, hey, there's an array list here, well, the idea that inserting into the front of an array list is going to take a lot more time than inserting in the back of an array list. If you don't understand what's going on under the covers, then it might be a little more confusing. So at least now you're getting the benefit of more knowledge. All right? OK. All right, singly and doubly linked lists. So remember, linked lists, the reason we teach them is so that you understand linked structures. And you'd be crazy not to learn a linked list, because you might get asked them in an interview. And if you said, no, we never covered those, then you probably wouldn't get the job. But so it's definitely linked lists have nodes that are self-referencing. In other words, they have a node contains a pointer to a node, right? And that's kind of the same with the trees and other linked structures. OK? You need to walk through the list to get to a value, obviously. You can't just jump there. This is not the random access that we like. Heads and possibly tails and special cases, all those special cases. Well, not fun to write code for that, but you guys got lots of practice of that on your homework. You do need to be able to reason through a linked list operation with a picture. OK? So drawing pictures is really super important for this stuff, as I mentioned almost every time I talk to anybody on that homework assignment. Right? You have to draw these things. So I could ask you to draw a linked structure. OK? And then you shouldn't understand things like this, that there's interesting things happen when you try to delete a node in a singly linked list. You'd better have access to the previous one, or you'd have to walk through the whole list again. Okay? Asymptotic behavior for lists, what's almost always going to be the answer? Linear. Can't do much better than linear in a linked list. Okay? So that's why it's one of the reasons it's not so good. Okay? All right, there are some benefits, right? If you're removing from the middle of a linked list, you just have to change one pointer. You have to get there first. That's the slow part, but then you have to change one pointer. Not that hard. Okay. All right. Doubly linked lists. We did that. It was the lab we did on that, right? Doubly linked lists, forwards and backwards, and this can be both a positive and a negative, right? It's great because you have access. You can walk the list both ways, right? You end up ripping your hair out when you're trying to write these things, right? Because you have to keep track of everything, and there's special cases with the head and the tail and all those special cases. This was the peanuts running lab. We did that. But deleting a node only requires the node. You get to that node, and you've got a pointer to the previous one and the next one, so you can change all those pointers. You just have to change 4 pointers every time. Yuck. And the operations can be tricky, the actual trying to figure out the details of that. We also have circular linked lists. We didn't really talk too much about those, but circular linked lists are these ones that the linked list, the tail points back to the head, and you can just keep going in one direction all day and get to anywhere else in the list. Kind of a nice idea. Useful, yeah. Amazingly useful, I don't know. not the, they're useful to a point. You should almost prefer like a circular queue to a circular linked list. Okay. What kind of question could I ask you? I could say, look, find errors in linked list implementation of insert before, right? I asked a question very similar to that a couple semesters ago, and it got mixed results. It's tough to find all these pointer errors when you're in a timed environment. It's just tricky. But that would be the question. We'll see some examples of that in a few minutes. OK, questions on linked lists? Any more questions on it? Right. What's your answer if someone says if a linked list is good or bad? Bad. OK, good. Don't say that in like an interview. A linked list good or bad? Bad. Why? I don't care. They're just bad. Don't say that. Right. You have to be able to back it up with something, right? OK. All right, now linear or recursion. So all of a sudden we get into this recursion, and we did spend a little bit of time on it. And you guys are doing lots of recursion for this homework assignment, right? Almost all the functions you're writing are recursive functions. Recursion is not magic, although sometimes it seems magical. It's a very interesting topic, I think, but not magic. It does take some time to understand, so you should try to really understand what's going on and practice like writing down. If you're doing like Fibonacci of 3 and you want, remember we did that on the board where it took like half the board to write down what was going on each time? Do that practice because you'll be able to then figure out what's going on. And I might ask you, what does this recursive function print out? Right? OK. They call themselves, the compiler takes care of the stack-like behavior. Remember, if you're calling a recursive function that calls itself, the one that returns first is the last one that you called. Okay, last in, first out. The last one you call is the first one that gets returned. Okay, stack-like behavior. You have to write and understand recursive functions. We'll look at a couple of these in a few minutes. And you should have some examples in your back pocket. The Fibonacci sequence. Remember, Fibonacci was terrible. Why was it terrible? Yeah. It was exponential behavior. Remember, each call, recursive call, called itself twice. Right? Not very fun. OK? Some of these other simpler ones. OK? I might ask you a little bit harder one. They asked for Comp 11 this semester. They asked a really hard one in the mid-year exam. It was tricky. It was print a number backwards. Not a string, a number backwards recursively. It was tricky. OK, here's a sample question. Write a... What? What? Did I miss something? Anyway. Write a recursive function to calculate the sum of the first n even numbers. Try it. Try it right now. Take a few minutes to do this. I actually don't have the solution. I guess we'll have to figure out the solution. Yuki, did you get it? Did you get it? Yeah. Good. Got it? Say again?
Do we need to know the difference between tail recursion?
No. You do not need to know tail recursion. You'll learn about that in probably programming languages class. We talked a little bit about it, but you don't need to know it.
Taylor recursion is like the same. It can be the same as doing it in a for loop, right?
You can turn Taylor recursion into a for loop very easily. Yeah, very easily. It's basically when the last line is the return statement. So you can basically store that, and then it makes making a loop very easy. Yeah. OK, who has an answer to this that they think is pretty good? Or something that's, OK, you could go for it. So I picked you on you earlier. OK, if n equals 0, OK, that's our base case. What are you going to do? Return 0. OK, I don't even need a bracket there. Return 0. OK. Return what? 2 times n plus some evens and what? Minus 1? Let's see if that works. OK, let's try sum even. And this is the part that you should probably be able to write out, right? Let's say sum evens, let's try 6. OK, sum evens 6. N is not 0, so it doesn't return. It returns 2 times. So this returns 2 times sum even of what? Sorry, I lied. 2 times 6 plus sum evens of n minus 1. So 5. I probably should have picked a smaller one. OK, let's do this. This returns 2 times 5 plus sum evens of 4. Turns 2 times 4 plus sum even of 3. Let's change this so we don't go through this whole million times. Let's see, 6, 5, 4. Let's do sum evens of 4. So 4, 4, 4, 3, 2. Whoops, 4, 3, 3, 2, 2, 1. And this one returns 2 times 1 plus sum evens of 0, which returns 0, right? Oh boy, OK. 2 plus 0 is 2. Plus 4 is 6. Plus 6 is 12. Plus 8 is 20. 20. Is that the sum evens? 4 plus 2 plus 0? No, not quite. Oh, I didn't return that. OK, the first n even numbers. You're right. So the first n even numbers, is that going to be, so n, it's so 2, 4, 6, and 8. 2 plus 4 plus 6 plus 8. Or does 0 count as the first even number? What's that? Well, it does, because then it would be 0, 2, 4, 6. No, it's not. You've got some 4 there. But we'll do it this way and just see. 14 plus 6 is 20. So that works if you say that 2 is the first even number. I guess it depends. The first even number is like negative infinity or something, right? But OK, that would work very good. Good, very good, very good. That would work. I mean, let's see. Yeah, I think that would work. Did anybody have a different solution, or did anybody interpret it wrong like I did? Yeah, I did too. It's a little harder, I think, it's a different answer if you are interpreting it differently. And if you interpret it to be 0, 2, 4, 6, you'd have to probably change this by n is 1 or something like that. OK, good, yeah. Well, I had read this wrong. I thought it was calculate the sum of the first, calculate the sum of like up to 4 even, 0 to 4. I just interpreted it wrong. But you can interpret it correctly, at least according to the way I read this. OK. Anyway, recursive functions like that, I will try not to trick you, but I do think you do need to understand the recursive functions. OK? All right. Good. Okay, stacks. So we've talked about stacks. Remember, a stack is just an abstract data type. You can implement a stack using other data structures, like a dynamic array or a linked list or something like that. Last in, first out behavior. Last thing goes in, the first out. You've got 4 basic things you can do. You can push. You can do top, which gives you the value but doesn't take it off the stack. You can do pop. We will interpret pop as giving you back the value and taking it off the stack. Okay, keep that in mind. I'll interpret pop being give you back the value and you can do it either way. It just happens that the standard template library doesn't give you back the value when you pop it, which it seems odd, but I guess there's underlying reasons that that's the case. And then isEmpty tells you whether or not it's empty. Okay, lots and lots of problems have a stack, either solution or formulation of the problem in that you can use a stack-based solution. Okay, postfix notation, converting infix to postfix. You won't have to do that, but that's the one with the parentheses to that postfix notation. And then tree traversal, of course, is one of the other ways we did that. You can't use tree traversal with a stack for level order. It just doesn't work. We use what instead? A queue. Okay. And what are the asymptotic behaviors of stack operations? Constant, right? All of them are constant, which is exactly why we like it. It's very limited, but constant. Good. OK, so that's stacks. What's a sample question? Explain the stack functions, right? Explain how to use a stack to perform post-order traversal. Discuss the asymptotic notation. Use a stack in a program to do something. So I might say, hey, solve the following problem using a stack, or 2 stacks, or 3 stacks, or whatever, right? And you'd have to be able to do that. Okay. I don't have a specific question in this case. Questions on stacks? They are really useful for lots of problems. OK, queues. We did that whole project on queues. You guys got sick of them. First in, first out behavior. Insert at the end, remove from the front, right? Just like a human queue. They're similar to stacks in that there's about 4 different things you can do with them, right? And they also have behavior of asymptotic behavior, of constant, right? You can do enqueue. You can get the front. You can do dequeue. Again, we will interpret this as dequeue giving you back the value, and an isEmpty function. Okay? You don't actually have to move the elements when you dequeue, right? You just walk an index down the queue, right? This is especially true for a circular queue where you have to worry about moving things to the back. Okay? Circular queues are great because you rarely have to expand them. If you're dequeuing and enqueuing at roughly the same rate, you'll never have to expand them. Okay? And the queues are the ones that we have to use for level order printing. Okay? All right. Questions on queues? You guys got a lot of practice on those. Should be able to think about queues in a number of different ways. Okay. All right. What's an example question? Write the functions to create the queue. Like I might say, here's some setup, and you need to write some functions that have queue behavior. You might have to write the enqueue, dequeue, isEmpty, all that. Okay. All right, and you should know how to do all that. We did have practice on that. Just a show of hands, how many people used a linked list in their queues for the homework assignment? A few of you, probably 10%. Not bad. How many used the dynamic array? Most of you. Anybody use anything else? You could have, maybe. All right. OK. All right, trees. So we did lots of stuff on trees so far. We're still working on trees. They're just nodes. They have children, right? A left and a right for binary trees. But other trees can have as many children as you deem necessary for your problem. Okay. Lots of vocab on trees. I'm not going to stress the vocab. It's not like I'm going to ask you to define these things. But you should know when I say something about them, more or less what I'm talking about. Right? We could have links to all the children. That's the hard one to code. Right? You could do that. But better if we just have, well, we could have like linked lists for those. That would work out. Remember, we did that with the directory structure. Okay? And that's what works for file systems. But trees are inherently good for recursion because of, just like the linked list, they are self-referential, meaning you can pass on a node, and recursively it generally works pretty well. Okay. There was a question on Piazza about coding something. It was like keeping the sum of the nodes or something. You could do all that, but it's so easy to write like a 1 or 2 liner to actually calculate some of these things. Some of those functions are like 2 lines long. When you think about it, you go, oh, that's actually not too bad. Very beautiful in that sense. Okay. All right. So then we do have these binary trees and binary search trees. Binary trees are just the left and right. Right. These are the ones you're going to see everywhere. Okay. They degrade into linked list behavior if you don't balance them properly. Right. They can anyway. If you're inserting into a random binary search tree, you're generally going to be OK, like random numbers in there. But somebody asked this in class last week, I think. If you're inserting into a binary search tree and you're inserting numbers in increasing order, well, they're just going to keep creating a linked list. It's going to go whoop down like that, right? So that's degraded behavior. Okay. We did look at an example briefly. I think it was really brief when we looked at this. Using a binary tree for arithmetic, right? Postfix versus to like interpret postfix notation in a tree. We looked at that. And then you can traverse them in all these different orders. You should know the difference between those. Okay, question?
Yeah,
Dexter.
what's the difference between a binary tree and a binary search tree?
Good question. You can answer that. Binary tree, or somebody else can answer that. Binary search tree has an invariant, which is what?
The ones on the right are larger.
Runs on the right are larger than a particular node. The ones on the left are smaller. That's the difference right there. Okay? Binary trees do not have to be binary search trees. But the opposite is not the case. Is the case. Binary search trees have to be binary trees. OK, let's see. We looked at an example using a binary tree for arithmetic. We show that in order. OK. Any other questions on binary search trees or binary trees? OK, binary search trees. These are the ones that are invariant, right? And average depth of a binary search tree is log n if it is balanced. Okay. Binary search tree methods you need to know. Find, min, find, max, contains, insert, remove, and removes the hard one. I will not make you code remove, obviously. You're doing that for your homework assignment. I'm not going to do that. And this is something that this came up a couple times in people asking me about questions. I forgot to mention this the other day. Lazy deletion in a tree. If you have a binary search tree and it's 7 and 20 and 2 and 18 and 30. If you're removing 20, the lazy way to do it, which I'm not letting you do for the homework assignment, the lazy way to do it is to keep another little piece of information along with this, or to make when the count, just say that the count can go down to 0. Guess what? If the count is 0, does 20 actually exist in this tree? Technically, no. Like it's there, but as far as the logic is concerned, it goes 7, and then a placeholder, and then 30, and then 18. Right? So you need to know that 20 is there so you can keep traversing in the right directions. But if you were to say, does this tree contain 20, you would return no if the count is 0. That's called lazy deletion. And it's nice if you don't want to do all these extra like removal things. But when you're talking about logarithmic behavior, it's not so bad normally. But that's all lazy deletion means. Okay, it just means don't actually remove it. Leave it there, but make it so the count's 0. Yeah?
So the only reason we would do it is if we were lazy?
The only reason to do it if we're lazy. Well, no. It's just saying that let's say you've got a tree of like 10, 20 billion nodes, right? And you're constantly adding and removing. It might just be just as easy to say, OK, every time if you're removing it and then adding it again and removing it and adding it again, just keep a count there. Then you don't actually have to do all this modification of the tree if you're balancing it. That's all. So there are some cases where lazy deletion makes sense. Okay. All right. Example, describe how to insert or delete from a binary search tree. Which one's harder and why? I think that's fairly standard. You guys are answering this on your homework assignment. Yeah?
I have a question.
You make a leaf point to a root. You mean like if the right of 30 pointed, or the left of 30 pointed to 7? Yeah, sure. It'll print an infinite tree, sure. Yeah. I mean, and you may run into that when you're actually writing your program, right, where it does that, right? This is now not really a tree anymore. Trees are kind of limited to the case where it's only one direction. This is now something called anybody know? I don't know if anybody happens to know what this is called now. It's called a graph. Yes, whoever said that was very good. Okay, it's called a graph. Now you've got links between. You have to be very careful that you don't do these things forever. Yeah, question and then question. Yeah.
So Scaling, do we have to know how to code it as well?
Do you have to know how to code it? Yes, but you're doing that for your homework assignment. So I'm probably not going to say double up on it and make you code it again. Probably not going to do it. Yeah.
Would this create an infinite loop? Like
Yes.
in our program?
This would create an infinite loop, right? Because you'd get to 30 and you'd go left and it would be 7 again. And then, now what do you do? Right? It depends what you're doing, but it could create an infinite loop. Right?
Would you ever want to do that?
Well, yeah, would you ever want to do that? Yeah, there are lots of reasons you would want to create a graph, yes. Yep. We'll talk about that near the end of the class when we get into some graph theory. But yeah, lots of reasons you might want to do that. Yes?
On the homework, there was a question on Piazza about creating a new node, but the syntax of new node, like the constructor,
Uh-huh.
even though the constructor wasn't written. I was wondering what the compiler does and how does it create a default constructor?
A default constructor doesn't do anything. It basically gets called and then, it creates a package for your class for whatever variables you have. So if you've got a left and a right, it will create pointers to a left and a right, but it won't fill those in with anything and it won't do any other details. It just does it won't set it to null automatically, no. You have to do that yourself. Yeah. Good question. Okay, anything else on these guys? Okay, AVL trees. Now I did promise you'll see something like this. I'm not going to trick you on this. You're going to see an AVL tree and you'll have to insert into it and do the proper rotation. All right, sorry if that's a spoiler alert, but that's all you're going to have to do, right? AVL trees are binary search trees, but remember the invariant now is that for a particular node, the left and the right subtree can differ in height by no more than 1. Okay? And then we have to do these rotations to actually figure out to rebalance if necessary. And you walk back up the tree until you get to the node that needs to be rebalanced, balance it. Here's an example. Okay, let's do this one right over here. Actually, most of it's the same, I think. Oh, not really. OK, so we've got 14 and 7 and 4 and 12 and 11 and what have I done? What the heck have I done? You guys got to fix me when I do crazy things like that. 7, here's the 12. 12 and 11, 13, 14. It's hard to see the board straight above me like this. OK, 53. OK, and we are inserting 8. OK, where is 8 going to go? To the left of 11, right? Because it's smaller, bigger, smaller, smaller, smaller. 8. OK. And so is the 11 not AVL? Or I should say, is the 11 AVL? Yes, 0 and 1. Is the 12? 1 and 1, 2. Is the 7? 1 and 1, 2, 3. So 7 needs to rotate which direction? 7 needs to go this way. OK, is it a double or single rotation? You guys are hesitant on this. Why is it a double?
It's the right child. No, it's the left child of the right side.
Yeah, it's the right subtree's left is where it went. So it's a double rotation, which means that which one do we rotate first? The child. So 12 rotates this way. We'll do that in a second. And then we can rotate the 7 the other way. OK? To rotate the 12 that way, which one do we grab onto? grab onto the 11 and don't change the link to the 12. And I'll just write it over here and then replace this for the interest of time. It's going to be 11 and then 12. And then the 8 is going to be here. And what's going to be to the, over here? The 13 is now going to be here. And notice we've gone whoop that way. OK? And then that would change this now. That would change this to be 11 and 12 and 13 and 8. And notice now it's as if you had a right insertion. So now when we rotate 7 this way, it'll work. So which one do we grab now? The 11 and shake it. And I'll write that over here. OK? So it's going to be the 11, and the 7 is going to stay, and then the 4 is going to have to be down here. OK, the 11 had an 8 there, so where's the 8 going to go? To the right of 7. And then here's still going to be 12 and 13. OK, and then the rest of this is actually going to be 14, 17, and 53. And let's see, is everybody OK now? 1 and 1, 1, 2, 1, 2, 0 and 1, we're OK. 1, 2, 3, or 1, 2, 3, and 1, 2. That one's OK. So we're all right. OK, see how that works? You're going to have to do a very similar thing on the test. Right? All right. Then we talked about asymptotic notation. Actually, we did this earlier, but we've talked about it through the whole class so far, right? Asymptotic notation, this is how we actually compare algorithms and data structures. We'll go over some examples. In fact, I'll focus on a couple of these examples in a few minutes. And then we compare these things using these primitive operations. But it actually, the way we do it in the big picture is much more broad than that. We don't need to worry about, oh, I mean, we mentioned it, we talked about it, that when you dereference an array, that's one operation. And then setting two numbers equal to each other, that's two. It's much simpler than that in R, like the way we're going to do it. All you need to do is say, how many times do how many of the operations are related to the total number of operations we have. So if there's one operation for every operation or every element in whatever structure, that's linear behavior, right? If you break a problem into half, that's logarithmic, all of those things. Okay? We disregard constants. The only one I said that you can't disregard a constant for is which one? Anybody remember? Tries. I do want you to know that the try asymptotic behavior is the length of the word, ordered length of the word, which really is constant. Okay? Yes?
Are tries only used with words?
Tries are generally used with words. You could have other things in tries, but anything that has a prefix, something with prefixes in them. And by the way, I've decided tries aren't going to be on the test. So we haven't even done a lab on them yet. That's next week. So you will not have to worry about that. Okay? All right. So here's the ones we care about. Constant, logarithmic, linear, quadratic, maybe polynomial, which would be like cubic or quartic or all that, and then exponential, the one you never want to have to write anything for, exponential. Okay, polynomial. The other one that's in here that we'll get to when we do sorting is n log n, but you don't need to worry about that for this. Okay? All right. And some hints on these. Constant does not depend on how many you have. N is linear, n squared is nested loops of n. And logarithmic is you break the problem in halves each time through. Okay? All right. So let me do this. Let me go to our website, Comp15. Google is so awesome, it just knows that this is the first thing I want when I do this. Whoops. OK, let's see. Comp15, we're going to go to the lectures, and I'm going to grab, let's see, lectures, and I'm going to grab, I put on here the midterm and the key. So if you want, check this one up first, and if you have a question, go look at the key. OK, so here's what's on the midterm. It's going to look very similar to this, where in fact, it's going to be like identical. So there was some array writing on here. In other words, write the insert at for a dynamic array. I had you write an expand. Actually, I had you debug. Last year I had them debug an expand function. There actually was, it says there were 3 mistakes. There are actually 4 mistakes in here. I actually had another mistake. Anybody find some of the mistakes? Yeah. I made a float into a new int array. Yeah, that would cause issues. Compiler would probably pick that up. Yeah. Square brackets instead of the parentheses. That was the one that I didn't catch. I don't know why I wrote that wrong, but I didn't even catch that one. All right, yeah. I don't update capacity. That's one of these ones where you're missing something, right? Yeah. Actually, you can't see it down here, but I didn't update the capacity on there. And then what's the other thing that I did wrong? Yeah. I deleted the array I just created. You guys laugh. How many of you did that the first time you tried to do this, right? You're like, oh, I got to delete something. No, you deleted one thing already. Don't need to delete the array. OK? All right. I love it. You're all laughing. Ha ha. Those Comp 11 students would do that. Ha ha. You know. All right. All right. Concepts. What's the difference between an abstract data type and a data structure? OK, so I'm probably not going to ask you this 2 years in a row or 2 semesters in a row. Imagine you're presented with 2 different data structures to evaluate and compare. Assume they have the same functionality to the end user. What would you want to consider? So this is like the thinking kind of problem. Like, what kinds of things do you consider when you're looking at data structures, right? Asymptotic behavior. That's the big one, right? You might also want to know how fast it goes and maybe how much space it takes up or something like that. There's things like that. OK, here's asymptotic behavior. We'll spend a couple minutes on this. OK, fill in the expected asymptotic behavior. What's the expected asymptotic behavior for this one? N squared. Ignore all the constants. Go to the big one that makes the most difference, N squared. How about this one? N fifth. OK, you might have to do this. I'll put the other one up too. Hang on. I think I had 2 in here. Yeah. So for this one, OK, what is the asymptotic behavior for the top one there? Think about it for a minute. Talk to your neighbor if you need to. All right, who thinks they know? Yeah. Yeah.
Log n.
Why is it log n?
Because you only, assuming that each item has a left or right, you'll be going to one of those each time.
Yep, you either go left or you go right. Now, if this happened to be a degenerate tree, it could be the worst case of linear, right? But I did say at the top, like, kind of your expected case. Normally, I won't ask you too many expected case ones, but in these ones, you should kind of say, oh, look, I get what's going on. This is a binary search, right? It happens to be searching through a binary search tree, and a binary search goes left and then right. Okay?
Couldn't this be also searching through a doubly linked list?
Could it be searching through a doubly linked list? Yeah, I guess it could. That would be linear. Yeah, that would be linear, but yeah, well, yeah, the problem with this one is that you need to have it sorted in some form or another to do the left and the right. So you'd probably have to think, oh, it's sorted. Yeah, if you had said linear and then put in parentheses, assuming doubly linked lists, I probably would have accepted it. Yeah, but yeah, yeah. Not always. I mean, we're generally going to worry about the worst case behavior. But in this case, I happened to say at the top, I said, think of the expected case. So I wanted you to just think a little bit more. And for these functions, the worst case is generally pretty easy. I want the expected case in more or less. How about the second one here? Anybody think they know? Yeah.
I think constant.
Why constant?
No matter what, it just does 1, 2, or 3 things.
Yeah. If the n is greater than the array size, in other words, this is like the error case. If n is less than 0, I'm just checking some number versus 0, return -1. Or I just return the array value, and this goes back to the random access. Am I walking through any arrays here? No, I'm not walking through anything, so I only have to touch one thing. So this is actually constant behavior. Okay, you should be able to look at these sorts of functions and try to figure out what they do just by making those kind of like calculations and things. Okay, yeah.
This is constant times like in the big O of n. We want 1 or 2 in the parentheses, like on the answer line.
This is big O of 1. Of 1. Yeah, you don't need to put 2 or anything. Just 1. Yeah. Okay. Yeah.
Just as a clarifying question, the last name is the name of the function, but it also means something in.
Yeah, that's a good point. I probably shouldn't have done that. Last name is the name of the function, but dot last name is the name of a property or a variable in there. It's not, if it had parentheses with all this detail, then you'd have to go, then it would be weird. It would definitely be a weird recursive function. I might ask you some recursive functions, but they shouldn't be too weird. Somebody asked me a really interesting one, put to me the other day. You might be here. I forget exactly who it was. They said, what if we did something like this in a recursive function that did something x of n minus 1 or something like that? That gets really weird. Like you could have a function x call a function x of n minus 1, which would be really weird. But I tried to walk through it, and it's definitely weird. The answers are not necessarily, you end up very easily going in infinite loops with that sort of thing. OK, so let's see. Then you're going to have to rank which ones are the fastest to second fastest, asymptotically speaking. Who knows how fast they'll really go, but asymptotically speaking. And let's see, linked list stuff. I'm going to make you do, there's the remove. Explain why it is possible to perform log n search with a sorted dynamic array, but impossible with a linked list, even though it's sorted. Not so bad. OK, and then more recursion stuff. So here I asked you to write a little recursive function on a tree to, given two binary trees, return true if they are structurally identical. In other words, if they're the same tree, return true. It's interesting. It was a good problem. I'd say about 80% of the class got it right. The rest were like, I don't know. And some stacks and queues stuff. Let's see. You can look at the answers to that and real life examples, and that's about it. Okay? So hour and a half. I am not going to be here on Wednesday. I'm going to be winging my way to Kansas City, Missouri. Anybody from Kansas City? No? I was going to ask if it's nice. I hear it's nice. There's a conference out there on how to teach computer science, or on teaching computer science, so it should be interesting. TAs will be giving you the exam. If you get, like if you have a question on the exam and the TAs can't answer it, and you think they should have been able to answer it, don't get mad at them. Just put a note on the problem saying, I'd like to talk to Professor Greg about it, and I'll chat with you about it. If that happens for everybody, we'll be in trouble, but I hope that doesn't happen. Yeah, Zoe. It's in this room, same time. Yeah, that's about it. Come on in here and try to sit at least one seat apart from each other, odd rows, that sort of thing. All right, see you guys. I'll see you Monday or in lab.